Hey everyone, today we're going to talk about two ways to verify hardware designs: simulation, the traditional approach, and formal verification, which is the mathematical powerhouse. Think of it like checking a book for typos. Simulation is like reading a few chapters carefully and hoping that you'd catch all the spelling mistakes. Formal verification is like running the entire manuscript through a spell checker that guarantees that no typo can ever sneak through. One is sampling, the other is proving. And that's the difference we'll explore today. Why does it matter? Because bugs aren't just annoying, they can be really catastrophic. In 1980, Therac 25 machine gave patients radiation overdoses. That's not a bug, that's a horror movie. In 1996, Ariane 5 blew itself up mid-flight because of an integer overflow. Imagine losing hundreds of millions of dollars because of a variable that couldn't count properly. And in 1994, Intel's Pentium chip had a division bug. Turns out, dividing numbers incorrectly costs about $1 billion. So, yes, bugs can be expensive. Simulation is like test driving a car. You try different roads, different speeds, hope that you covered enough, but you'll never drive every possible road. Formal verification is like hiring a mathematician to prove the car can't crash ever, no matter what road you take. It's more about airtight guarantees than running different tests. This diagram shows the state space traversal by both dV and Fe for an example case. So the circles represent the clock cycles or the uh, state of the system that can be reached after every clock, starting from the reset state, which is the green dot at the center. The four lines show different scenarios which can possibly be covered by dV. And the red and the blue dots represent all possible states in a particular cycle. As you can see, also the red dots are the bugs and blue are the non-buggy states. As you can see, design verification or normal DV, a simulation-based DV, can trace a few paths and it can cover, say, 3 out of the 6 red uh, buggy states, and it can uncover those bugs. Whereas formal, given that it reaches a particular, the checks run reach a particular cycle or particular bound, can cover all the 6 possible red dots. In short, if we can guarantee the absence of bug once it completes the run, or once the check passes a particular so-called cycle or bound, whereas DV cannot. Theoretically, if we had infinite time, simulation would cover all possible test cases, and if we had infinite computing power, formal verification would cover anything, everything. I mean, but since we don't have infinite anything, except maybe bug reports, we can combine both approaches in reality. Formal verification has one big villain: state space explosion. That's when the number of possible states becomes too much that the formal tools can't cover all possible scenarios or reach the state where the bug is present. To fight this issue, we use tricks like abstractions, decompositions, and other smart strategies. Abstractions mean you simplify parts of the design which is not relevant for the check, or which is relevant but you still keep a smaller version of the design for simplicity. Decomposition is breaking big problems or checks into smaller ones, and other strategies like using formal only where simulation is proven to be not sufficient. There is another concept to remember: bounds or clock cycle, the concept of bounds. So simulation runs for certain number of cycles covering a particular test sequence, and formal it works on the concept of bounds. Let's say if you have a property and it did not fail for bound or cycle 10, then the only guarantee you can give is that if the system is starting from a particular state that is specified, then if it is run for 10 cycles, or like if it goes to bound of 10, there will not be any bugs. That guarantee is what you can give. You cannot give any guarantee that it will not there will not have any bug after that. We call it bounded pass. If we can justify that up to 10 bound 10, if it is enough to prove that there are no bugs, then we can safely say that it is sufficient. The formal run is sufficient. We can call it bounded pass. And if it fails, if the check fails, then you get something called a counter example trace, and where you can see a scenario where a failure exists, or you can trace the path to that buggy state. Think of it like the difference between I drove 10,000 miles without crashing versus I proved mathematically that I can't crash in the first 10 turns. So in the industry, here are the common approaches to integrate FE. You can use FE on blocks where DV can't possibly generate enough meaningful test cases in time, or you can use FE for even the final sign-off process, which is the process to give guarantees for the design that there are no bugs, or you have done enough tests so that you can proceed with enough confidence to tape out the chip. You can use FV in that process as well if you're confident about the formal bench. Well, what is formal? Formal is just it's not a single magic trick. It's more like an orchestra. So you can play different instruments which are playing their different parts. So let's say property checking will is something that you use to prove some rules always hold. You write properties, you write your own checks, and you ensure that it does not fail. Equivalence checking is something where you ensure that two variants of the design or two versions of the design are same in terms of certain functionalities or most of the functionalities. Data path is another way of data path. Formally some other track. Informal, it is used for some data intensive units like floating point floating point units. And then there are theorem proving concept, the idea of theorem proving where you bring in a lot of math, get your hands dirty more. uh, you do more involved math. And then there is another track called architectural formal. So each track tackles different flavors of bugs. So together they are like the Avengers of verification, stronger as a team than alone. And this is one of the options, one of the possible flaws that you can use in formal. Before we go into the slide, there are some prerequisites. So when we refer to as property, or like property informal, we can be referring to as three variants of properties. One is called assertions, where you write a property which is supposed to be always true, or which is supposed to be true for the conditions that is specified in the property. And if it fails, that means you need to debug and you need to find out issues and you need to fix your environment or so-called assumptions or constraints in the design, or fix the design itself if you find an actual bug. The second type of property are covers. A cover property is like asking, is this corner case even reachable, like in any scenario? Or an example could be, can FE454 ever become full? So things like interesting scenarios for which you want to see a trace. Assumptions are constraints to the environment. Uh, you want to make sure that you don't formal uh, formal takes any kind of crazy input which is not at all functionally possible, giving you a lot of false failures, taking a lot of your time. So you can apply constraints which makes the input or the external world behave in a sensible way for the design. Now that said, let's go into the formal verification flaw, or one possible flaw. We start with we start with reading the microarchitecture spec or the architectural reference manual, and then come up with a plan on what to verify and what are the timelines and what are covered in the scope and what are not. Once we write enough number of checks and they are running okay for a few days, like say 1 or 2 days or something, then we start to check. We can, or in parallel also, you can start to check if we miss something. For there are multiple approaches for doing that. You can try injecting bugs yourself, or you can try to reproduce the bugs which are already now filed by somebody else, let's say simulation team. Once you're confident, you can move on to checking even more scenarios, even more sanity checks. You could run regressions and see if the assertion, if your checks are reaching enough bounds. So this is called bound analysis. And here, this is how it's done. You have a check that says that a particular functionality is correct, and then you write a bunch of cover properties that will hit the scenario through different paths or through different combination of inputs. You don't specify input in formal, but somehow you specify that this functionality is, uh, let's say, activated through different paths. And once you have all these covers, you can find look for the longest bound, look for the bound which is the largest among all these covers. And if your original assertion or the check is reaching or going past that bound, you can be confident that hey, I covered enough scenarios for this verifying this functionality, and maybe this is enough. And the last step is to verify that. So in the process so far, we would have introduced a bunch of assumptions, or constraints in the environment. So you need to make sure that you're not over constraining the design, or you're not running in an environment which is incorrect. You're missing, if you're adding an assumption or constraint in such a way that you miss some input combination to the design, which is actually forcible in the real life scenario, then you might end up missing a bug. So there are a few ways in which you can verify those assumptions. One would be to run the assumptions in the DV simulation runs itself. But then, hey, DV doesn't cover all the scenarios that will be started formally in the first place. So you might end up verifying all your assumptions there as well. So I don't have a solution for that. And second, use the ARM architectural reference manual itself to verify the assumptions. After all, that's the golden reference that you have. Assuming the architectural reference manual has enough specifications, or you have an architectural reference manual to begin with. If you're verifying a CPU, it is straightforward, but if you're verifying other blocks, it might not be. Assuming you have such a manual and you have some pseudocode or some text you can compare against the assumptions, then that would be a way to go. So what tools can you use? There are various tools, a lot of tools in the industry, but some popular ones are Jasper Gold from Cadence, VP Formal from Synopsys, and then open source tools like Symbiosis, NUXME, and a lot of other tools, which these are just for the formal property verification and data worth formal verification. If you want to do theorem proving, then there are other tools which I'm not talking about. And that's that. We have seen why bugs can be so costly, how simulation and formal differ, and how they work together. Well, a little bit of that. Formal verification may sound intimidating, but it's really just another tool to save you from a $1 billion headache. Thanks for watching.